We're going to talk about one of the more challenging things that we do in this part of the course on vectors is vector projections. So the vector projection of u, otherwise known as vector PQ, onto a non-zero vector v, which we're also going to call PS, is the vector PR that I'm going to show you in a moment, determined by dropping a perpendicular from Q to the line PS. So let me show you a couple different ways this could look. So here is one version, is where this is our starting vector PQ. So this is the P and that's the Q. And our vector PS that we are going to project onto, I'm going to say at first here is kind of short. So there is our vector PS. And the second way we can look at that is I'm going to try to now make PQ look the same direction and the same length as the first one. So you're going to have to work with me here. And on this one, though, the vector PS is not short, it's really long, but it's still going in that same direction that the other one is. So the idea here is we want to project PQ onto vector PS. And PS may be different lengths. But what we want is to drop that perpendicular down to the line containing PS. So in this case, PS is too short, so we, extend it there to get the line, and then we're going to drop the perpendicular down to that line containing that vector PS. And that's our point R right there. And likewise here, now the PS is way too big, but that's okay. We're going to drop that perpendicular down and call that the vector R. So what we're saying then is that this vector PR is our projection vector of PQ onto PS. So what we're seeing then is this has a couple of interpretations or meanings here. So one thing we can say is, I'm going to decide what color I'm going to go to here. So I'm going to say one thing we can say is we have resolved our original vector u into components PR and, I can squeeze it in, PR and RQ with PR perpendicular to RQ. So what this is saying now, in general, what we have said in the past, which is true, is that we could imagine starting with like an XY axis, and then we can take any vector we want and we can resolve it into its X components and its Y components. That is, we can say this vector going here is the same as going X vector in that direction of the x-axis plus this Y vector in the direction of the y-axis. But there's nothing really unique about those axes, about the x and y-axis. We could also say that we could take our vector PQ and say, we have part of it, the red part, is going in the direction of the vector PS. And remember, this RQ can be slidable. I don't know if it helps to see it this way. But we could think of then RQ, which is perpendicular to PS. Then we see that the red part is how much of our vector PQ that's going in the direction of PS. And the blue vector is how much that is going perpendicular to that, much in the way that we have seen here when we resolve a vector into its x and y components. So that's one thing that we can get. Now, from this, we can also see that the u, our original vector, that's our, remember, our PQ, that's another name for PQ. So u is equal to the PR, that's that projection vector onto PS, plus the RQ. Right? You can see that, going tip to tail, we add those together and we get that vector that we started with. And so just as we see in, we look over here in component form, if I called this vector, say, let me just call it M for no particular reason, then M is going to be that vector in the X direction plus that vector in the Y direction. Okay, we're doing that, but with different components than the X and Y axis. Now, the second way of thinking of this, or some more information, I guess, the standard, whoops, I lost my pen there. The standard notation for vector PR, the standard notation, this is going to be a little bit strange at first. We're going to have to get used to it. The standard notation for vector PR, which we are calling the vector projection, of U onto V. So remember we took PR, which we called in a short form as U, and we said PS, which in short form is V. So the projection of U onto V is given by, and here's our strange notation. So we said it was vector PR, and that is we write PROJ of V onto U. So that's the projection of U onto V. So I'm sorry, we say the U, so we say projection of U onto V, and the V is the subscript. That's the one we're projecting onto. Now you can also see then that once we know what this PR is, once we have figured out what that projection of U onto V is, we can see that U, that's that vector we called PQ, is, we can say that RQ, so RQ is going to be the original U minus its projection vector. So the projection of U onto V. So we're going to be asked to find that a few times. Okay. So I may need a new screen for this. So I'm going to move to a screen here, and we're going to ask the question now, how do we find this projection vector of U onto V? So let's look at our picture here. So here is going to be our vector U. This is the one we're going to project, and we're going to project it onto V, and I'm going to, just to make it easier to visualize, I'm going to make V longer than we need it to be, so it's nice and long. And this is our angle theta. That's the angle in between U and V. And so we can see, visually anyway, our projection vector. If we drop the perpendicular from U down to V, then this is going to be our projection vector right there. So that is our projection of U onto V. And I'm going to call that, right now, I'm going to say that, I'm trying to figure out what color to make that. I'm going to say this length right here, this length right here, I'm going to call W. So that's the length of that projection vector. Okay, let's see what we know. So we know that the cosine of theta, the cosine of angle theta, is going to be U dot V over magnitude U times magnitude V. Is that okay? So remember, V is the green and U is the yellow. Now we also know from our right triangle trig, so we also know another way of getting at that cosine of theta. We can say that the cosine of theta from our SOHCAHTOA is going to be the adjacent over the hypotenuse. And the adjacent is going to be that magnitude of W over the magnitude of U. So let me, I didn't label that very clearly. Let me think of that as being a vector. Okay, so since those are two different ways of getting at that same cosine theta, then we can, in this second expression here, we can multiply that magnitude of U to the other side and get the magnitude of that projection vector is going to be the magnitude of U times the cosine of theta. Now we're going to come back over here and we're going to replace the cosine theta that we see in yellow by this stuff. And so this is now going to be the magnitude of U, and that cosine theta we're going to replace by U dotted with V over magnitude U times the magnitude of V. And so we can see that we can cancel those magnitude of u's. Those are the same number. And so what we're getting is that the magnitude of our projection vector is going to be this U dotted with V over the magnitude of V. That's a big first piece of this puzzle. Okay, so that's telling us that length of that red vector that we can see up in the picture. Now, as a little bit of an aside that we're going to bring into play here shortly, we know that a unit vector, so a vector of length 1 in the direction of our vector v that we're interested in projecting onto, in the direction of vector v, is given by, and on right equals there I'm going to say is, so it's going to be vector v divided by its magnitude. We talked about that earlier. So this is now going to be a vector in the direction of v of length 1. So that's going to make our projection vector. So our projection of vector u onto v, which we have also in our schematic up here called w, is going to have the length of that vector, which is in the blue there. It's going to be u dotted with v over the magnitude of v, and then times, and maybe I shouldn't use that dot, that's just a multiplication symbol, times vector, the unit vector in the direction of v. And so this is going to become, when you look at that denominator, we're going to get u dotted with v over the magnitude of v squared times vector v. Okay, that is our projection vector. Okay, that's what it is in general. So we see our magnitude of the projection vector of u onto v given by this blue expression, and our actual, I'm going to rewrite it over here, our actual projection of u onto v, remember this is a vector, is given by this. Now, something worth noting is that, so one way of thinking of this is what this represents is how much, I'm going to go back to the original direction up here, the original picture up here. So what we see the projection vector represents is how much of this yellow vector u is going in the direction of the green vector v. So this has some importance we're going to see, for example, in work. So if we're trying to move an object in the direction of the green vector v, and we're going to apply the force in the direction of the yellow vector u, then what we're going to see is that the red vector w is how much of that force that's really doing what we want it to, that's moving in the direction of v. And then the perpendicular to that, which we have talked about before, it doesn't look very perpendicular there. So the perpendicular to that is going to be, in effect, force that's wasted. It's not really helping us move that object at all. Okay, so let's see if we can actually do an example. So here's our first example. Find the vector. Oh, wait, I gotta back up. First, so I'm gonna erase this. I'll try to erase that. Okay, so now something to note is that so we had our projection vector of u onto v is given by this u dotted with v over the magnitude of v squared times the vector v. So it's a vector. Now, if v is a unit vector, so if v is already a vector of length 1, then this is even more simple than the projection of vector u onto v. We can see that this part right here, if v is a unit vector, that magnitude of v is just 1. 1 squared is just 1, so we're going to get that we just get this u dotted with v times vector v, or that the magnitude, if we want to know if v is already a unit vector, the amount of that vector u that is going in the direction of v is exactly its dot product. So that's a nice kind of application or understanding of what a dot product really is. When you dot something with another vector, you're seeing how much of that is going in the direction that you're dotting it with. Remember, we said if u dot v is 0, that means that the vectors are perpendicular, which makes good sense because if the vectors are perpendicular, then nothing is going in the direction, nothing of the vector u is going in the direction of v. I hope that makes sense. Okay, let's go now to our example. So let's say find the vector projection. So find the vector projection of u, which is going to be given by 6, 2, onto v, which is the vector 5, -5. Then write u, so write our vector u as the sum of two orthogonal vectors, one of which is that projection vector we just found, the projection of u onto v. Okay, so let's see what we got here. I think a picture might help us a little bit here. So here's our axis, and let's say that I want to make u into this yellow vector. So I'm going to go 6, 2, let's say right here is vector u. And then I'm going to make vector v, the green vector, so it's going to be 5, so 5, -5 is going to be down here. So here is our vector v. So we're imagining, I'm going to have to turn my head here, we're going to project u onto v, and we're looking for this vector right there. That's our projection of u onto v. Remember, that's a vector. Okay, so to do that, we're going to need to know, we want to find that this vector is going to be u dotted with v over the magnitude of v squared times vector v. That's how we're going to come up with that vector. So that means u dotted with v. So up on top, we're going to get 6 times 5 plus 2 times negative 5. There's our u dotted with v. The magnitude of v is going to be 5 squared plus 5 squared, square root of that, turn around and square that, times our vector v, which is this 5, negative 5. Hope you're with me here. So that is going to become, let's see, we got 30 minus 10 is 20. 25 plus 25 is 50. Square root of that squared is just going to be 50. So that's going to be times our vector 5, negative 5. And so that's going to be, in this carefully constructed problem, 2/5 times 5, negative 5. And dividing by the 5 is going to make that be 2, negative 2. That is our projection of u onto v. Oops. Okay, so now we also, so that's the first part. We found the projection vector. So we've done that first part. Now we want to write u as the sum of two orthogonal vectors. So we want u to be equal to our projection vector, 2, negative 2, plus this orthogonal vector, I'm going to just call w. So that means to find w, we're going to take our original vector u and subtract off our projection vector. This is what we do all the time. So that orthogonal vector, let's see, the u we were told was 6, 2, and minus the 2, negative 2, and so that's going to make that orthogonal vector, let's see, 6 minus 2 is 4, 2 minus a negative 2 makes that 4. So we are saying that our vector u is the sum of those two, where it's the sum of these two vectors, and that's what our w is. Okay? All right. I think that's going to be good to go.